Today we're going to talk about another very cool algorithm. It's called linear programming, and it has many applications, a really great historical story, and you'll see that once you learn how to use it, you can solve many, many interesting problems. So let's start with the simple experiment. This is the type of linear programming problem I think you've probably encountered. It's an optimization problem. I'm going to call this guns and butter. It's a famous economics idea that society must decide how to spend its resources. Does it build guns? Does it build a military? Or does it build a fat society? Sort of like a general, like essentially, does it care for the people and let them have plenty of butter? Resources are scarce, and so one has to decide how much of your general resources you spend on one versus the other thing. And in particular, this is the main issue of the presidential election this year. How we take our collective resources and invest them, and what do we invest them in. So one can formulate this type of question as follows. X represents the number of guns you have, and Y, let's say, represents the amount of butter you have. And you'd like to maximize the sum of X, Y, or in particular, you might even put a coefficient here and maximize like 1 times the amount of gun and 100 times the amount of butter that you produce. But there might be a few constraints. So for example, you might have 10 units of metal, and a gun takes twice as much metal or electricity or whatever as a unit of butter. And so the 10 units of this physical resource that you have, the amount of guns and the amount of butter you have to produce has to be less than 10. There might be other constraints like this, for example, which might be like a morality constraint, okay? So as a society makes more guns, then but these stories are just not very good. But this is nationalism, okay? Let's call it like that. Because as you make more guns, you get, you spend a little bit of that nationalism capital, and as you make butter, sort of that gives you a little bit of extra. I'll just stop right there. Now, if we want to solve this linear program, one thing we can do is start graphing these things. We know 4x minus y has to be less than 8. So if we graph all of these constraints, I'll go ahead and graph them like this. We know that the feasible region, that all of these linear constraints create a feasible region right here. Now the question is, we want to maximize the x plus y of these type of constraints. And so what we can do there is we can draw the line, we can draw these lines which all represent x plus y equals some coefficient, okay? And we'll notice that right here, the x plus y line right here intersects this point right here. And so we know that the maximum x plus y value that we can get right here is going to be this particular point right here. And so in a two-dimensional guns and butter problem, you can take your maximization equation and your set of constraints and geometrically solve this type of problem. And now what linear programming is going to be, linear programming is going to be a generalization of this idea to many variables. And a priori, it doesn't seem extremely powerful, but through the next 5 examples that I'm going to show you, as we generalize this, 2 things are going to happen. First, we can express many, many problems. In fact, any polynomial time algorithm you can express as an LP. For many problems that we've already studied, it actually gives a very concise and very simple description of that problem. So that's one thing. It's a powerful tool. The second thing is actually finding an algorithm that solves an LP. That has been quite an interesting intellectual problem. So the problem was posed in the 1940s by a guy named Danzig. He did it by hand to solve a number of interesting problems that I'm going to discuss with you. And then since then, there has been basically a long series of attempts to find a polynomial time algorithm for this. And the first one who did it was this guy Carmarker in the 1970s, but it's a very complicated algorithm. So we're going to stop by me showing you a very simple way, a simple high-level idea for how to solve LPs. And we're mostly going to focus on the applications of this technique. One of the nice things about this LP is that it's this certificate of optimality. But if we want to actually figure out what the maximum of x and y could be subject to these constraints, if we were able to magically guess, for example, 7 right here and -1 right here, and we multiplied both of those equations, we would get something like this. 14x plus 7y has to be less than 70, and negative 5x plus 2y has to be less than or equal to 2. And now if we added up both of those equations, you'd get that 9x plus 9y has to be less than 72. And so in particular, that implies that x and y has to be less than 8. And indeed, if we look at this graph right here, and since it's drawn properly, we see that the optimal solution, all of these lines right here, are bounding a region. The feasible solution set has to be within this region right here. And the maximum, when we're trying to maximize x plus y, is this point right here, which is 8. And here is a pretty simple argument that you can't get any larger value. I've taken the constraints, and I've taken a linear combination of them and shown that the max this value could be has to be 8 if it's still going to satisfy these constraints. This idea is what's going to allow very large instances of linear programs to be solved efficiently. We're not going to go to exactly how that is used, but this is in particular the idea. So he went back to the Pentagon, and the Pentagon was like they were looking for something for him to do. And then in 1948, a story I'll talk about, the Berlin airlift, basically the Russians blockaded Berlin, and that created a very important problem for him to solve. And he in particular used that technique to introduce this idea of LPs. In 1979, this guy came up with the first polynomial time algorithm. This guy came up with a simplification, a separate one. And in 2006, this guy, Daniel Spielman and Keller, those guys found a randomized simplex algorithm. We're going to talk about a simplex one. They came up with a very simple algorithm for which they could show a linear time algorithm for this particular problem. So it's been a very long time that this problem has been studied. The start of it was the Berlin airdrop. So at the end of World War I, Berlin looked like this. Both Germany and Berlin looked like this. Essentially, Berlin was broken into 4 parts after 1945. And the Soviet Union had all of one part of Berlin, and in particular, it also had the rest of Germany. So Berlin was in East Germany, and so there was a small part of Berlin which was occupied by the Allies, and the rest of Germany was occupied by Russia. And that was essentially the treaty in 1945. That's how they decided to split everything. And in 1948, the Russians, in the summer of 1948, the Russians decided that they would just put a barricade around all of the ways into Berlin. So all of the roads they closed, all of the trains they closed, all of the rivers they closed. What the Russians were expecting was that if you could not supply that city, basically the Allies would give the rest of Berlin to the Soviet Union, and that would solve a big problem for them. And what the Soviet Union was not counting on was this idea that there was still an airport in Berlin. So there's one airport in Berlin, and the Allies decided that they were not just going to give up Berlin like this, they were going to make a stand. And so they decided to ship in all of the goods that were necessary for that entire city. It's a city of like 300,000 people, and it was in July. Whatever coal, whatever food they had, and whatever electricity, whatever other durable goods that this city had, medicine, etc., they were eventually going to run out unless they were replenished. And so the idea was that there were several hundred airplanes that from Europe would basically fly into Berlin, drop up supplies, and then fly out. At the peak of this campaign, a plane was taking off every 45 seconds from the Berlin airport. So they were dropping off and then dumping stuff and then flying right back off. And the flow of planes out of Berlin was one every 45 seconds. And this involved a massive logistics problem, because people realized that, for example, coal, which is the most important heating, so the winter was coming and they needed to basically heat the whole city, some of these planes were just full with coal. For some of you who come from that part of Virginia, you know that coal is not a nice material. It gets dust everywhere, and it's like slightly corrosive. It destroys things. And so coal would basically start eating through the wires of these airplanes every once in a while. These airplanes would start failing, and they'd have to be cleaned at some point. That's one constraint. After 5 flights of putting coal in there, you have to clean the whole inside of it and get all the dust out. Otherwise, the wires of the plane would deteriorate. Another type of things are pilots and the type of airplanes that you have. Some pilots can only run on certain type of airplanes. And so that's a constraint that, for example, you have with an assignment problem, that we have in the homework, that's one of these things. Only pilots that can fly the planes can be assigned to those particular planes. Additionally, the time of loading and unloading a plane makes a big factor as to how much material you can get in and out. So what Danzig did is he wrote down about 55 constraints that reflected the physical parts of this problem. And then he decided to schedule all of the airplanes based on this type of linear programming to try to maximize the amount of stuff which they can bring to that city of Berlin. And it actually succeeded because in the end, essentially, they showed the Soviet Union that they were willing to do this ad nauseum, and so the barricade was basically given up. Thanks to the logistics that this computer science problem enabled. Another problem that was developed at about the same time is this problem called the Stigler diet. And so this economist for the US Army decided that they would think about what it actually takes to feed a soldier. Because when you have an army, in fact, feeding the army is one of the main logistics problems that every general since Julius Caesar has encountered. This guy decided to take a scientific approach and said, you know what, a soldier needs 3,000 calories, of which this much has to be protein, calcium, iron, vitamin A, etc., etc., etc. And if you get all of those materials, then you'll have a very healthy soldier. The question is, how cheaply can you feed a soldier? And so what this Stigler person did is he took a table, and this is turned sideways. Basically see like this is wheat flour and this is like cornmeal. He basically considered every ingredient that the army could get their hands on. And then he measured how much salt, how much protein, how much it cost, how many calories per unit, how much vitamin A per unit, etc. He made a very big table of all of the goods that were available to him, plus what their nutritional components would be. And then he formulated what was called the Stigler diet, which was the most efficient way to feed an army person. And it was like basically pennies. If you gave them like, you know, a bunch of peas and some other things, you'd basically formulate them. So I thought what I would do is show you an example, and this, I think, is going to be called UVA diet. And to simplify, I think there are about 4 things which in my experience, most of you have consumed. Brownie, that's both the normal kind and the special kind. And then the dumpling truck, which I see lots of you eating from. And coffee, which I'll just purify in terms of espresso. And then, of course, this roots, which is really delicious. Each of these particular things costs a slightly different amount, and they have different calories. And, of course, the requirements for a UVA undergraduate is to make sure that you have enough calories, which let's just say is 500. You have chocolate, you have sugar, and you have fat. Those are the other real important ingredients in your diet. And now let's try to figure out how we can optimize your experience here at UVA. So what we'd like to do is minimize the cost that you actually incur to feed yourself. And so let's call this variable x1, x2, x3, and x4. And so what we're going to do is minimize the cost. We want to find out how much brownie, dumpling, espresso, and roots you should consume. And we want to minimize the cost of each of those, subject to the constraint that you have a healthy life. So for example, now at this point we want to make sure that 400 calories times x1 plus 200 calories times x2 plus 150 calories times x3 plus 500 calories times x4, we need to make sure that you have at least 500 calories. We want to make sure that you have at least 6 ounces of chocolate and 2 ounces of sugar, 10 ounces of sugar, and 8 ounces of fat. Okay? So this right here is a linear program that allows you to optimize your diet. And this type of programming, where you basically minimize some linear objective function subject to a bunch of constraints, it can model many interesting problems for you. So one of them is right here, the Stigler diet or the UVA diet problem. Now, another way to write that, as you can see, is as a matrix right here. So this A times X has to be greater than or equal to B. We can always formulate the constraints in terms of this matrix, right? So here, 4 times x1 plus 200 times x2 plus 150 times x3 plus 500 times x4 has to be greater than the number of calories. Similarly, we need to have this much chocolate, this much sugar, and this much fat in this particular program. So I wanted to illustrate how you could actually solve this problem. In practice, what you would do is take a program like this with its coefficients and represent it. This is how you would encode it right here. You'd basically say that you have 4 variables, that's x1, x2, x3, x4, and you have 8 conditions. And so in particular, what I didn't write is that also you can't have a negative amount of brownies. As much as a dieter would like to eat negative brownies, it's not possible. We want all of these values to be positive. And so we can basically describe these constraints. There's a negative here, like in standard form we want this to be greater than or equal to. The program that I'm using has a different standard form, and so this is just a lower bound, and so these values are multiplied by -1. Oh, I think this has to be an 8. But this is how you would basically represent this matrix program in terms of an input to a linear program solver. Then you just run the solution, and the solution would give you this right here. It would give you the optimal value, which says you should buy 3, if you want to meet this diet restriction, you should have 3 dumplings and an espresso. And moreover, it would give you a certificate of optimality right here. If you multiply all of those constraints by these equations, just like I did before, it would show you that the most you could get was 9. Now in this case, I think I ran the slightly wrong program, so the actual solution to this would be slightly different. But this is how one would actually run these type of problems. What I wanted to do was find the cheapest lunch possible that satisfies my constraints of what I want in a lunch. And this linear program is saying the cheapest lunch that one can get that satisfies these conditions is $9. And it involves ordering 3 dumplings and an espresso. Let's consider some other ones. We've solved the shortest paths problem using Dijkstra's algorithm or Bellman-Ford algorithm. Now we're going to solve it as a linear program. So the input is going to be a graph and edge weights. And the output, as we've discussed, would like to be a dv for each vertex in the graph, where dv is the length of the shortest path from S to V. Okay, and you're also given this source. Now, a priori, it's not clear how you can represent a shortest path problem in terms of constraints like we've discussed. What I want to show you is that a very simple program actually does it. So if we define dt to basically be the sum of all the dv in the graph here, 3-line program basically explains exactly what a shortest path is. And it's kind of counterintuitive. So let me explain. What we're going to try to do is maximize the sum of the distances. Even though we're minimizing shortest path, we're going to solve this by maximizing dt. And it's going to be subject to the constraint that dy minus dx has to be less than or equal to the weight of the edge between x and y for every edge in the graph. And of course, the starting node is going to be starting as ds equals 0. So let me show you an example. Here is a graph, and I'm going to claim that the values that I've assigned here are shortest paths. And in particular, when we take the sum of all of these values that I've assigned, this, by the way, is the example that we had in the Bellman-Ford lecture. So the sum here, the maximum I could make this, I claim, is going to be 30, because if I try to increase any particular number here, I'm going to fall afoul of this particular constraint. This constraint guarantees that I can't cheat and make this number larger. So for example, suppose I try to make this number 5, because certainly in this particular case, the distance between 5 here and 0 is, if I assign it 5, it's certainly going to be less than this particular 5. But on the other hand, I can't assign this value 5 because between I and h, di is 7, and dh is 5, so 5 minus 7 will be -2, and -2 is not smaller than -4. Sure, and that's if I want to do it with as Dijkstra's. And I can do this as well with negative edge weights as long as there are no negative cycles. It doesn't detect negative edge weights here, but, or actually I guess it would, because it would show that the problem is not solvable. But yes, this can handle negative edge weights too. So it's kind of counterintuitive, but what we're asking is kind of like this natural property. We want shortest paths. What this is basically saying is that dy has to be less than or equal to dx plus L of xy, right? And that was a property that we've discussed quite often when we're talking about shortest paths. It's sort of like the key idea. And if we make sure that this holds universally over the entire graph, then if we try to maximize this dt, it actually gives us these labels which turn out to be the length of the shortest paths. If we minimize these things, so this is the thing about LPs, you have to kind of think about things in a funny way. If you put minimize dt, then you could just make these things arbitrarily negative, right? You can put these to negative infinities, and all of these things would still be true. Put this as negative infinity. Certainly, it still satisfies that constraint, but if you minimize dt, in this problem, if you minimize these things, you don't get an answer. There's no tension in the system. This is kind of like trying to hold strings. This is a physical analogy of what's happening here is you're kind of holding strings. You're holding all of these nodes and letting them fall where they fall, right? And there's a tension of trying to increase the sum while making sure that you can't extend past the shortest path lengths. Yeah, exactly. So that's why there's a tension to try to increase it and a constraint to try to make the distances reflect some sort of natural property like the edge lengths. This is kind of the idea behind max flow min cut. You have something you're trying to maximize and something you're trying to minimize at the same time creates a tension, which the technical term for that is duality, and that's what kind of allows these algorithms to work. Let's consider max flow. How would we express max flow as an LP? What we want to do is maximize the flow that leaves the source. So we can basically say maximize the sum over each vertex of FSV minus, and it's going to be subject to a bunch of constraints. The constraints are FE has to be less than CE for every edge, and the inflow of a node is equal to the outflow. So the sum of the flow into a node minus, and finally, the flow has to be positive or zero. We can actually solve problems that go beyond the problems we've studied so far. So let me give you one example. Let's say you have a max flow problem, but in addition to the source, the sink, and capacities, you also have a price function. So the price function tells you for each edge how much it costs to send flow across that edge. And so if you think about a flow problem like a communications network, Google, there's a recent story that Netflix moved all of its cloud storage from Amazon to its own system. Dropbox moved all of its storage from Amazon to its own systems while keeping the system alive, running. And so you might consider this is Dropbox, this is Amazon, and this is Dropbox, and you want to move all of your files from one big system to another. You want to do it as fast as you can, but you also want to do it as cheaply as you can. So there may be several ways to route that traffic, and one might then consider how we find a min-cost max flow for a particular graph. And so this value d right here is the max flow value. So one could solve this problem by first solving the max flow on the graph without looking at prices. That would give you this value d. And now we can formulate a linear program that helps us find the minimum cost flow that achieves this flow, right? So what we could do, for example, we could min the flow on each edge times, so let's say FE times XE, right? So these are prices that are given, subject to the constraints that we had before. So first of all, we want to make sure that the flow is still the maximum. So previously in our previous LP, this was the thing that we were trying to maximize. But once we find a particular value for it, we can basically set it to be this value. And then, of course, we can have the same constraints as before. So this is how that problem could be modeled. Here are the rules of the game. On LP, put them in what are called standard form. So a standard form LP is something where you're trying to maximize some value x, and x is essentially a vector here, x1 all the way up to xn. You give it as a vector here. These are constants, so this is part of the problem that you specify. You're looking for x, but you're given this c. So you're trying to maximize this dot product. Okay, so one can also write this as basically xc, like that if you want, transpose. And then it's going to be subject to a constraint like this. You're going to take a dot product of these xi's, and they have to be upper bounded by bi. And each of the values have to be positive. So this is what an LP, this is how you specify a linear program. Let me argue why specifying a linear program like this is without loss of generality. So suppose if instead of a max problem you had a min problem. How could you formulate this as a max problem? We've done it before in class. That's equivalent to just max of x of negative xi times ci. So any minimization problem you can formulate as a maximization one. What happens if instead of this being an upper bound, you have it as a lower bound, right? So remember in the standard form, in a standard form, the constraints have to be upper bounds. And what happens if you want to show a lower bound? Again, you can multiply by -1 and get this. What happens if they're equality? What if you need to make this equal? How can you express that as an inequality? Yeah, so what you can do is give two inequalities. So you can certainly say it has to be less than or equal to bi, and transformation slowly. Both of these to hold. That enforces equality. So then what you can do is multiply this by a negative, multiply this by a negative, and that changes this into... There's one other constraint right here. We basically require each of these values to be positive, and that's really not an issue either. And you can do this very simple trick, which is to basically, if x doesn't have any constraint, you can replace x with two variables like this, where both x prime has to be positive and x double prime has to be positive. If you wanted to allow x to be negative, you would just substitute x with this expression right here. And let's say you wanted to be -100, right? That was the optimal. Then you could basically find positive values for x prime and x double prime, which make this -100. So any problem can be expressed in this standard form. And now let me show you something, a very, very cool application of this. These are called zero-sum games. In game theory, we can often simplify interactions by saying, look, the row player Rowena and the column player Colin, they have a set of actions. So in this previous example, we can play rocks, papers, and scissors. So Rowena can, of course, play rock, paper, or scissors, and Colin can also play rock, papers, and scissors. And this is a zero-sum game because either Rowena wins or Colin wins. And we can write the payoffs for each of the outcomes in this matrix. So of course, if we both do the same thing, then we tie, and so nobody gets anything. But if I play rock and you play paper, that means that since paper beats rock, I'm going to lose $1 and you're going to win $1. But of course, if I play rock and you play scissors, then it's going to be vice versa. So here's a simplified version of this game. And it's zero-sum because in each of these boxes, I win and you lose, or vice versa. When you have zero-sum games like this, you can simplify the game. It's sufficient just to say what the row player wins when this is the outcome. So if Rowena plays this and Colin plays this, then the row player gets 3, and obviously the column player gets -3 to make it 0. So when we have games like this, it turns out that we can use linear programming to decide what the optimal play in a game like this would be. So if both Rowena and Colin are rational players, what should they do? How should they play? We're going to be able to use LP in order to formulate this problem. There is going to be some optimal strategy for Rowena and Colin. And that strategy is going to lead to a value of this game. So Rowena is going to play R1, R2, Colin's going to play C1, C2, and so the outcome is going to be with probability, and these are probabilities, and so the outcome of the game is just going to be with R1 times C1 probability we get 3, this is what Rowena gets, and with R1 times C2 probability we get -1, and with R2 times C1 we get -2, and with R2 times C2 we get 1. So this right here is called the value of the game. This is how much Rowena expects to get from it for this particular strategy profile. And so what do you think a fair game is? A fair game is one like rocks, papers, and scissors. Fairly intuitive to say that when we play rock, papers, and scissors, what my value from that game is basically equal to my opponent's. Right? We both have an equal chance of winning that game, and there's no unfair advantage. In a game like this, though, there might actually be an advantage to be the row player versus the column player. Which player seems to have an advantage here? The row player seems to have a slight advantage, but by how much? How much would you pay in order to be the row player in this game? $1? All right, so this is what LP could actually help us figure out. So this right here is the value of the game. Let's imagine, as a thought experiment, Rowena decides to say, here is my strategy. Here's what I'm going to do. And if it's an optimal strategy, she might as well. When Rowena answers R1 and R2, yes, R1 and R2 are the probabilities with which Rowena plays either top or bottom. What do you think Colin can do? Colin can either play left or right here. And if he plays left, he's going to get 3R1 minus 2R2. Okay, that's if Colin plays left. If he plays right, he's going to get minus R1 plus R2. And notice Colin gets the negative amount of this. And so what Colin is going to want to do, he's going to want to try to minimize this value. He wants to find whichever one is lower, I get the opposite of that. So if for example, the value is -1, Colin gets $1, right? So he's looking to minimize this particular value. So this is what Colin can get from the game. And what Rowena is going to try to do here is maximize whatever Colin does. What Rowena can hope to get from this game, let's call this value Z. Now, the reason I wanted to go through this is I wanted to explain how zero-sum games represent things like poker that you might play in practice. And here is a sketch of how one can represent poker as a linear program and try to solve it. At least 1/7. Because look what program I'm maximizing the value. If I announced my value R1 and R2, I tell Colin, hey, this is what I'm playing. You can do whatever you want. Colin is going to try to do as well as he can. And so we know that Colin is going to try to minimize that value. Colin is going to try to minimize, if I say I'm playing R1 and R2, Colin is going to try to minimize this value. And the solution of my program says, no matter what Colin does, okay, because I've expressed what Colin is going to try to do, I'm going to call this value Z. Whatever the value that Colin does is going to be Z. And I want to maximize Z, subject to the value that Z is going to be the smaller of this or this. So no matter what Colin does, I'm going to be able to guarantee that I get Z. And in this case, it's 1/7. That is, yes, that because these strategies are randomized, it doesn't mean, it means that the expectation, my expected value of this game is 1/7. So I'm going to play, according to my strategy here, of picking this with 3/7 and picking this with 4/7. Now, in some times, I'm going to win 3, okay, because I picked to do top and Colin picked to do left, okay. But sometimes I'm going to actually lose 2. But on average, if I play 3/7 and 4/7, okay, no matter what Colin does, my expected value is going to be 1/7. And in particular, if Colin does the optimal thing, which is playing this, then I will get expected 1/7. Yes, if I knew what Colin was going to play, if Colin had told me, oh, by the way, this time I'm playing left, then of course I would say, oh, there's no linear program necessary. If Colin is playing left, I'm going to play top, because that's the maximum there. But that's not how games usually work. What I wanted to do was try to explain how one could use this formulation of zero-sum games to do something possibly interesting to you if you play poker. So remember the way I described Liar's Poker is too big a game because you have too many cards and too many actions and so forth. Liar's Poker is a simpler version. If you recall from last class, the way that you play Liar's Poker, let's say this is Alice and this is Bob, and these are their secret hands. They hold those dollar bills to their, they kind of keep it secret, okay? And these are the cards that Alice is dealt. She's dealt 2 7s, 2 6s, 2 5s, 2 4s, and an 8. So this is a pretty good hand right here. And meanwhile, Bob basically has this hand. And now, in the first move, remember, Alice can do a few things. She can basically say, I have 1 1, 1 2, 1 3, 1 4, 1 5, or I can say I have 2 1s, or I can say I have 9 1s, or I can say I have 9 9s. Basically, Alice has 81 moves here, right? In the second step, Bob has to either call. Bob can say, no, I don't believe that you have 1 1. Please show it to me. Or Bob can raise. So Bob can say, no, I have 2 1s, or I have 3 1s, or I have 9 9s. So at each of these particular moments, so for example, at this one, Bob has 81 possible moves. But for example, at the extreme end, when Alice says she has 9 9s, all Bob can do is call. And so Bob only has 1 move here. But in many of these trees, Alice then has a next move, and then Bob has a next move. And in general, this is called a game tree. And this game tree is really big, because the first set I have 81 moves, and then I have 80 moves, and then I have 79 moves, etc., etc. And the game can go up to 80 steps before someone has to call. So this game is enormous. In principle, it's still a zero-sum game. So if I look at Rowena, here's what I'm going to do, and if Bob does this, here's what I'm going to do. In principle, Alice can write that whole thing down. She can write down, first I'm going to say I have 2 2s. Then if Bob says he has 3 2s, I'm going to say I have 5 2s. Then I'm going to call. That's a strategy, and she can basically enumerate all of her strategies. There's probably like S to the 80 to the 80. Okay? And similarly, Colin can write all of his strategies over here. And in each box of this matrix, the value is either going to be 1 or -1. Either Alice is going to win or Bob is going to win. It's a zero-sum game. And so in principle, one can take this program, the program that was, this was a 2-move game, right? Row only had 2 strategies, row 1 and row 2, and Colin only had 2 strategies. And we wrote a program that had 4 rows right here. In principle, one can take this very complicated game and write it as a matrix like this and come up with a program that is of size 80 to the 80 squared. Okay? So in principle, one can take, the next thing to do is notice that this is too big a strategy, but you can prune many of the stupid strategies that are always going to lose. You can always say this is dominated by this other strategy, so I never play those type of things. So you can try to prune this game and simplify it dramatically. Here's a natural question about Liar's Poker. A natural question. What is the value of the game? Just like in that previous game, we saw that Rowena has a strategic advantage in that game. She's going to win. That's not a fair game. It's Rowena wins with 1/7. So if we knew what the value of the Liar's Poker game is, then we would save all of the hedge fund and investment banker people a ton of time and energy. because they would no longer play the game. They would realize the game is not fair. The person that makes the first move either has an advantage or has a disadvantage, and essentially the game becomes solved. Just like, although my children love to play tic-tac-toe, I'm not sure if you continue playing that game, right? Because you know that the game is always a draw. Games like poker are still fun because we don't know whether there's an inherent advantage to the, to the big blind. We don't know. And solving smaller cases of this, I mean, there needs to be some interesting computer science to solve this type of problem. It is an LP. In theory, it can be solved. It's too big, so someone has to make some sort of mathematical analysis to improve it. And several people have, but I'm not sure that there's a definitive solution to either Liar's Poker or the full game of Texas Hold'em. Now, casinos do this all the time. They hire mathematicians to figure out each of the funny games that they have. They have thousands of variations of this and that, and they add all these complications to games like blackjack, where you can do this and that. You can hit the green button. If they hit the green button, you have this. You can do it. If you've ever gone to a casino, you know that blackjack is not just like, let's just play blackjack. There are a bunch of complications, and those have to be analyzed in these type of things. Question? Yes. So as my office mate Chris did in graduate school, he bucketed many of the strategies for Texas Hold'em. He said that when I get 4 or 5 unsuited, I'm just never going to play. So he just throws out a lot of these. He throws out a lot of particular things and tries to come up with a strategy that's bucketed, that results in an LP that's reasonable size, and that takes like a few days to solve, and he tries to solve it and figure out what that strategy is. Now, I think depending on what approximations you make, you can show that there's a slight advantage. If you do optimal play, there's a slight advantage to being the dealer, or the person right behind the dealer, and under the assumption that you throw away many of those hands. So people have done this. Group in Alberta is I think the leaders in this. They've tried to analyze this. It's an AI problem fundamentally. This LP type of thing is trying to build agents that interact that interact with people, and you want to try to come up with rational strategies for agents that work in these type of zero-sum games. And so this is how you kind of formulate it. I wanted to introduce this because LP is a very important tool. It's used all over the place for scheduling. It solves most of the problems that we've just talked about with graphs. And you can use it to model some pretty interesting things. FedEx uses a more complicated version of this to route all of their packages every day. And of course, these tools are totally accessible. You can download the source code on this particular page and solve these LPs. Let me try to give you a hint of how these solutions actually work. So this is the simplest algorithm. It's a greedy algorithm, and it works in practice, but its exponential time is the analyzed running time. So what you do is you initialize at the origin 0, 0. And that's why we move programs to, if we create programs in standard form, then we know that 0, 0 is a feasible solution. So 0, 0, 0. And while a neighbor has a higher value of c times x, remember CT is what you're trying to do, okay? The idea, and I'll show you graphically, is to start at a feasible solution. And that usually starts at 0. And then you just move to progressively better solutions. And that's inherently the greedy algorithm. So this is a greedy algorithm. And it works in practice, but it has exponential time in the worst case. And in this case, the worst case can actually be problems that arise in practice. And as I said, there's been a lot of theory that's very complicated for solving this problem in polynomial time, and that's that. We're going to talk about how the simple solution actually works. Let's take a look at a problem here. Max of this value subject to these particular constraints. So notice that x and y, x and x2 have to be positive, and this constraint means that the solution has to be to this side. I'm going to progressively show the 4 constraints. And notice that 0, 0 begins as a feasible solution. It's within this region right here of feasible solutions. We'll have to go back to this one. Do you think that the optimal solution can be somewhere in the middle here? Any point in the middle here since this maximization is a sum of two positive values right there, you can always increase one of the values in one direction or the other here and get to a constraint right here for which this objective function will always be larger. The first idea with this linear programming is that the solutions, the optimal points, are always going to be at these vertices. Now, in 2 dimensions, if you have n constraints in 2 dimensions, how many vertices are you going to have? You're going to have n squared vertices, because a vertex is just going to be the intersection of 2 constraints. I take any 2 of these lines, draw them, and they're going to either intersect or be parallel. That's why it's O of 2. It's upper bounded by n squared. I can pick any 2 of them, intersect them, and that's going to be a vertex. Now, what about if you have n constraints on n over 2 variables? How many vertices you're going to have? Close enough. It's going to be n choose n over 2, which what you said is a big upper bound on that. I take any of my constraints, and this is the dimension. N over 2 is the dimension that we're working in. So if you think about in 3 variables, you take any 3 hyperplanes, you intersect them, and you get a point. Right? Any 3 slices in 3 space, when you intersect them, you're going to get a point. And so if you have n over 2 variables, you pick n choose n over 2 of them, and this is going to be exponential in n. So the interesting thing is, as the dimensionality of this problem increases, as you have more variables and more constraints, you can't just inspect all of the vertices and find the one that maximizes your objective function. But you can actually do this thing where you start at some particular vertex and you try to make a path that increases the value of your objective function. The simplex worst case is one of these crazy looking objects in high dimensional space where you actually have a staircase where you sort of spiral around really, really slowly, always getting slightly better, but it takes you exponential number of steps to get to the highest point. Now, there are much fancier ways to try to do this. One of them is called this ellipsoid method. Another is called the interior point method. Both of these are using some fancy geometry to try to improve the number of steps you need to take. Question in the back. You never have to look at the inside. You always start at a vertex, and then you try to get to a better one. So let me try to illustrate this. Okay, so here's our program. And we're going to start here at x1 and x2 are going to be, you're going to start right here. Okay? And now look at your objective function. If I want to grow that value the fastest that I can, which variable should I increase first? x2, right? x2 right here has the highest coefficient here. And so if I increase x2, I'm going to increase the value of this function. So in particular, I want to try to increase this value as much as I can. And now what is going to stop me from increasing x2? So for example, this constraint right here, when x1 is 0, this means that x2 has to be, x2 can be infinity, right? x2, this constraint has no constraint on x2. This constraint right here says that x2 has to be less than 4.5. This blue line right here says that x2 has to be less than 4.5 right here. That this final constraint, this bottom constraint right here, it requires x2 to be less than or equal to 3. It is the most constraining version of the problem. So what we're going to do is we're going to replace this constraint, right? Before we had x1 is equal to 0 and x2 is equal to 0. And now we're going to replace this constraint with this constraint right here. And the way we're going to do that is via a change of variables. So in particular, we're going to say y1 is equal to x1, but I want to set y2 such that this variable right here is tight. So I want to set that one to be 3 plus x1 minus x2. So in particular, if I substitute this back in, and so now what I'm going to do is go through this original program and replace everything that had x1 with y1. So a similar version of this program is going to be 2y1 plus 5 times 3 plus y1 minus y2. And the constraints are going to be 2y1 minus 3 plus y1 minus y2 is going to be upper bounded by 4. y1 plus 2 times 3 plus y1 minus y2 is going to be less than or equal to 9. And negative y1 plus. So the next slide, I've done that arithmetic as a check, right? 2y1 plus 5y1, that's 7y1 minus 5y2 plus 15. And that's exactly what this is right here. Now, given this program, which variable, and by the way, our solution is still 0, 0, but it's now with respect to these new variables y. And now, which variable should I increase right here in order to improve the score the most? Clearly y1, right? And so I can go through each of these equations again and figure out which variable is going to constrain y1 the most. And here y1 can be at 7. Here y1 is going to be constrained to be 1, right? So it's going to be this one right here, which is the tightest constraint on y1. We can again define z to be, and make that substitution. Okay? And that substitution would lead to this program. Now the reason we're doing it this complicated way, because look at this expression. What can I do to increase the value of the max? What we've realized right here, z1 and z2 are both equal to 0 in this program. And increasing z1 or z2 will strictly decrease this value. So in particular, what this has told us is that the max of this program is 22. And if we go and look at this diagram right here, indeed, the max right here happens when x is 1 and y is 4. And if you plug that in, it's 2 plus 20, 22. Take a look at these coefficients right here, 7/3 and 1/3. And now if you multiply this one by 7/3 and this one by 1/3, you're going to get 7/3 x1 plus 14/3 x2 is upper bounded by 63 over 3, and negative 1/3 x1 minus is going to be. So not only did we find a solution here, we knew that we were done because these coefficients are all negative, and so we can't get any larger. And moreover, these coefficients right here give us a proof of optimality. Okay, great. So this is, the origin is optimal if and only if c is negative. And c happens to be these coefficients that you use right here to compute the optimal function. There's many other small problems, like how do you find initial vertex? The program, you might have to shift the program to make sure that 0, 0 is a solution. What happens if there's no solution? Some LPs don't have a solution. They're unbounded. You can get them as large as you want. You have to know when that condition occurs, and then the runtime of this problem as well. Question?